you likely hold a mental picture of an atom shaped by countless familiar diagrams and depictions. At its heart, a tiny spherical nucleus resides, orbited by electrons in a manner strikingly similar to planets circling our sun. It's a tidy, uncomplicated concept effortlessly drawn, and this exact visual representation populates almost every science textbook. Walk into any science museum, and you'll spot a model hanging overhead, miniature spheres affixed to rods, meticulously tracing flawless circular trajectories. However, here lies the crucial revelation: that widely recognized portrayal is, at its very core, profoundly flawed. It's not merely a minor inaccuracy, it's not good enough wrong. It is wholly, utterly, and fundamentally mistaken, to an extent that should compel you to re-evaluate much of what you believed you understood from your education. An atom bears no resemblance to a miniature solar system. Electrons are certainly not diminutive celestial objects. Should you endeavour to grasp the genuine mechanics operating within an atom while clinging to that visual, your efforts are doomed to futility. You will find yourself thoroughly bewildered. You'll formulate inquiries for which no responses exist, precisely because the very premise of those questions rests upon an untruth. Therefore, permit me to reveal the authentic reality that truly inhabits an atom. And I must forewarn you, what I'm about to describe will likely challenge your comfort zone. For what genuinely manifests within is so profoundly bizarre, so completely at odds with intuitive understanding, that your intellect will undoubtedly push back against my elucidation at every juncture. Our journey commences with the most elemental of atoms, hydrogen. One lone proton, one individual electron. That constitutes its entire composition. This particular atom is universally utilized for illustrative purposes, specifically due to the assumption of its inherent simplicity. You probably picture the proton situated centrally, a minute sphere, possibly measuring 10 to the power of minus 15 meters across. The electron, meanwhile, is positioned somewhere in its proximity, engaged in an orbital motion around it, perhaps 10 to the power of minus 10 meters away. The very first question that arises: what is the electron's exact location? Your intuitive response might be, it's presently on the atom's left flank, following a circular trajectory. But that is incorrect. The electron does not occupy that particular spatial coordinate. The electron, in fact, has no precisely determinable location. The challenge isn't rooted in any deficiency of our precise measurement techniques, nor does this phenomenon arise from any imperfection in our scientific apparatus, no matter how sophisticated. Intriguingly, the electron itself fundamentally possesses no singular fixed location until the very instant it is observed. This isn't merely an abstract philosophical musing. Its nature is not subject to individual subjective interpretation. Indeed, this is precisely what the foundational mathematical framework unequivocally dictates. Moreover, this profound truth is consistently affirmed by a multitude of repeated experimental observations. The electron, in its unobserved state, inhabits a peculiar quantum phenomenon known as superposition. It is not confined to a singular exclusive point in space. Instead, it concurrently occupies various potential positions, existing both here and there simultaneously. The electron's presence is distributed as a diffuse probabilistic cloud, enveloping the atomic nucleus. At this juncture, you might be tempted to simplify, thinking, all right, so it's merely a cloud then? You might envision the electron as physically diffused, much like butter spread thinly on toast across a specific region of space. But no, that particular mental visualization remains fundamentally incorrect. The electron itself is not physically diffused or spatially extended in that manner. Upon the act of measurement, the electron instantly manifests as a discrete, singular point particle. Yet prior to any direct observation, it possesses no definite or fixed spatial location. What is actually distributed is the probability or likelihood of detecting it at various points throughout space. A mathematical construct known as the wave function precisely delineates the probable locations where one might detect the electron upon observation. In specific regions where the wave function's magnitude is substantial, the probability of finding the electron there is consequently elevated. Beyond this, the odds of its presence are exceedingly slim, a mere whisper of probability. Within certain defined areas, the probability of its existence vanishes entirely. It is an absolute certainty that the electron will never be found in that precise location. Yet brace yourselves for an idea poised to fundamentally reshape your perception. Before any measurement, the electron isn't merely tucked away in one of those regions of high probability. It's not secretly residing in a specific spot, its precise coordinates merely eluding your knowledge. It genuinely occupies no singular fixed point in space. The electron, at its very core, embodies the wave function. This and only this defines its complete reality. Now let us turn our attention to orbits, for this is precisely the point where the comforting solar system analogy utterly collapses. The common mental image is of the electron tracing a pristine circular path around the nucleus, ceaselessly, akin to a car on a continuous circuit. Regardless of its velocity, be it swift or unhurried, the underlying presumption is that it's unequivocally progressing along a distinct trajectory. However, this foundational premise once again turns out to be fundamentally flawed. This is precisely where the central challenge emerges. Were an electron to truly trace such an orbital trajectory, it would, by its very nature, be constantly accelerating. Any entity executing circular motion is, by definition, in a state of acceleration, even if its speed is constant, purely because its direction vector is perpetually altering. What's more, charged particles that are accelerating consistently radiate energy. They release light. This stands as a core tenet of electromagnetism. This phenomenon is completely quantifiable. This particular phenomenon manifests. Consequently, a truly orbiting electron would incessantly shed energy, radiating it outward as light. As a direct consequence, with every decrement of energy, its orbital trajectory would inevitably constrict. The electron would plunge in an ever-tightening spiral, inexorably drawn closer to the nucleus, its velocity escalating until a cataclysmic impact. It would inevitably strike the proton, and the entire atomic structure would utterly disintegrate. What precise duration would such a rapid process entail? Let's perform the necessary computation. The calculated time frame is approximately 10 to the power of -11 seconds. That's an incredibly brief 100 trillionths of a second. Every single atom throughout the entire cosmos would, in theory, disintegrate almost instantaneously. Yet it is abundantly clear that no such event actually transpires. Atomic structures in reality exhibit remarkable stability. They simply do not undergo such a rapid disintegration. Consequently, the electron simply cannot be following a classical orbital path. All right, you might reasonably contend. Perhaps then it isn't tracing a perfectly circular orbital path. Perhaps it's merely remaining utterly motionless, at rest, held firmly by the nucleus's electromagnetic attraction. However, this proposition is also fundamentally incorrect, because if the electron were truly at a standstill, we would be able to ascertain its precise position and momentum with absolute certainty. Its exact location pinpointed precisely at that singular point. Its momentum is observed to be precisely zero. Quantum mechanics unveils a core principle. It's impossible to ascertain both values with absolute precision at once. This deep-seated notion is exactly what's termed the Heisenberg uncertainty principle. Significantly, this does not represent a simple flaw in our measurement instruments. Instead, it exists as an inherent foundational characteristic embedded within the very essence of nature. If one attempts to pinpoint an electron's exact location, its momentum immediately turns vague and unpredictable. Conversely, should you endeavour to precisely ascertain its momentum, its spatial coordinates subsequently become indistinct. The cosmos simply does not permit the simultaneous knowledge of both. Thus, the electron is neither elegantly circling nor is it merely stationary. Therefore, what precisely constitutes its condition or behaviour? Astonishingly, it performs no actions in the traditional understanding of the word. Its foundational condition is merely that of unadulterated being. It appears as a wave function, an intricate mathematical formulation that delineates likelihoods. Moreover, this wave function is defined by specific permissible configurations and discrete energy levels. These unique configurations, vital for atomic architecture, are exactly what we term orbitals. An orbital, it's essential to understand, is not a static, singular entity. Furthermore, it does not represent a distinct trajectory or a foretellable course. Rather, it delineates a particular spatial zone where the electron possesses the highest probability of detection, accurately described by its wave function. Let's examine the most basic orbital, that of hydrogen in its lowest energy state. It displays flawless spherical symmetry. This cloud of likelihood is most concentrated immediately at the nucleus, progressively thinning as one ventures further away. Cast aside notions of rigid orbits or exact paths. Instead, envision a shimmering cloud of probable positions. When energy levels rise, these electron orbitals assume progressively stranger and more intricate shapes. Certain ones manifest as familiar dumbbell-like structures. Intriguingly, others present themselves as distinct donut-shaped configurations. A significant number reveal elaborate designs characterized by multiple, well-defined lobes. It's paramount to grasp that these are not tangible, solid physical constructs. Instead, they represent probability distributions, functioning as conceptual maps that pinpoint an electron's probable location at the moment of detection. However, brace yourselves, because this is precisely the point where the behavior becomes genuinely extraordinary. The electron, contrary to intuition, does not undergo a gradual transition from one orbital state to another. There is no gentle progression, no seamless glide from its fundamental ground state into an energized, excited configuration. Instead, it executes an instantaneous, abrupt jump. This remarkable occurrence is precisely what we designate as a quantum leap. In a single moment, the electron's wave function inhabits the arrangement of the lower energy orbital. Subsequently, in the blink of an eye, it adopts the shape of the higher energy orbital. No transitional phase exists. There is absolutely no unbroken continuous shift. It simply does not traverse the empty expanse that lies between these two separate orbital configurations. It merely performs an abrupt, seemingly inexplicable transition. Yet, by what mechanism does it accomplish this feat? That particular aspect, my friends, continues to be a profound enigma to us. Nevertheless, the underlying mathematics precisely and elegantly describes this astonishing phenomenon. This phenomenon is consistently corroborated by direct empirical evidence. Yet we possess no discernible mechanism or explanation for how an electron leaps from one point to another, seemingly bypassing the space in between. It simply operates in this peculiar fashion. Now let us confront the electron's true essence, for this is precisely where our conventional understanding begins to unravel, leaving us profoundly unsettled. Conventionally, we picture the electron as a minuscule spherical entity, complete with its own mass and an inherent electrical charge. Though incredibly tiny, it is nonetheless considered a concrete entity, a distinct object, a fundamental building block of matter. Yet when put to the test in experiments, we uncover a startling truth. The electron also displays behaviours strikingly similar to those of a wave. Most remarkably, it exhibits the astonishing ability to interfere with itself. It can curve and disperse around barriers, a clear demonstration of diffraction. It holds the power to spread widely and then later converge, perfectly mimicking every characteristic action of waves. So what then is its ultimate identity? Is it a discrete particle or an undulating wave? The answer is it is neither. Fundamentally, the electron does not conform to the definition of a particle, nor can it be precisely or fully characterized as a wave. Instead, it manifests as a quantum entity, an object utterly devoid of any direct classical analog. It's an entity that reveals particle-like attributes under specific experimental conditions and wave-like attributes under different ones, yet at its core, it is intrinsically neither. When not directly observed, its behavior is perfectly encapsulated by a wave function. This wave function progresses fluidly, expanding, interfering with itself, and executing every characteristic action we associate with waves. And yet, the moment the electron is measured, the instant it's actually detected, what invariably appears is a localized particle, a sharp dot on a screen, or an unmistakable click from a detector. Never a dispersed extended wave-like distribution. The very act of measurement is what precipitates the wave function's collapse. That nebulous cloud of probabilities instantly crystallizes into a single unambiguous outcome. The outcome is pinpointed right here, with no other possible location. A solitary point strictly confined within a particular region. Yet the precise mechanics behind this event remain an enigma to all. What genuinely constitutes a measurement is something no one truly grasps. Moreover, the ultimate fate of the wave function after its collapse remains entirely unknown. This profound dilemma, dubbed the measurement problem, has baffled physicists for nearly a century. Numerous interpretations have surfaced, many worlds, pilot waves, and objective collapse theories. Nonetheless, these remain purely theoretical interpretations. The foundational mathematics operates flawlessly, its predictions consistently aligning with experimental outcomes. Despite this, we still lack a clear conceptual understanding of what's genuinely transpiring. Now, let's further complicate this already intricate situation. Let's now introduce additional electrons into our theoretical framework. Picture helium with its 2 electrons, lithium with 3, carbon with 6, and iron with 26. One might initially presume that all these electrons are engaged in orbital motion. No, wait a moment, they are not in fact orbiting. Instead, they all exist simultaneously as wave functions enveloping the atomic nucleus. However, here's a truly critical aspect to grasp. These electrons are utterly identical. They are completely, perfectly, and fundamentally indistinguishable. It is entirely beyond our ability to tell them apart. Their sameness isn't a matter of mere resemblance or strong similarity. Instead, they are fundamentally one and the same. Electron A and electron B are not separate entities that merely happen to possess identical characteristics. Instead, they are the self-same entity, simply appearing in 2 distinct locations. This foundational truth carries with it truly profound implications. If 2 electrons are interchanged, the wave function of the entire system experiences a sign reversal. It gains a negative multiplicative factor. This is no trivial detail. Instead, it stands as a foundational principle. This phenomenon is known as the Pauli exclusion principle, and it is the very reason matter exhibits its solidity. It's the fundamental explanation for why you don't plummet through the floor, why atoms possess their intricate structures, why chemistry operates, and indeed why life itself is even conceivable. Crucially, no 2 electrons are allowed to occupy an identical quantum state. Should an electron reside in a specific orbital with a defined spin, no other electron can exist in that precise quantum configuration. Consequently, they are compelled to layer themselves, occupying distinct orbitals, thereby constructing the very framework we recognize as the periodic table. Absent this rule, every electron would inevitably collapse into the lowest possible energy state. As a consequence, every atom would exhibit identical chemical characteristics. There would be a complete absence of complexity, no molecules, no chemistry, and ultimately no you to experience it. But what then is the underlying reason for this? What mechanism compels the wave function sign to reverse when identical particles are interchanged? The exact cause continues to elude our comprehension. It is simply an empirical rule that we have discovered through observation. The mathematical forecasts consistently align. Experimental findings corroborate, yet a deeper understanding remains elusive. Now, our focus shifts to the nucleus, a constituent you might mistakenly deem uncomplicated. Simply a dense aggregation of protons and neutrons. Minute, spherical entities merely clinging together. That concept is yet again erroneous. Protons and neutrons are not, in fact, truly elementary. Instead, their composition involves quarks. To be precise, each contains 3 quarks. These are up and down quarks held together by the formidable strong nuclear force mediated by particles known as gluons. Nevertheless, the quarks residing within the proton are anything but static. Instead, they appear as quantum fields, constantly fluctuating, interacting, and incessantly exchanging gluons. The proton does not merely contain 3 quarks, as a bag might hold marbles. Rather, the proton forms a bound state of the quark field, a stable pattern of oscillation. And now, prepare for a truly astonishing revelation. The bulk of the proton's mass does not originate from the quarks themselves. Indeed, quarks are nearly massless. The predominant portion of its mass arises from the energy of the gluon field, which binds the quarks together. Energy at its core constitutes mass. Consequently, when you contemplate the query, what truly constitutes a proton? At its very heart, the fundamental explanation is energy. More precisely, we're talking about bound field energy. It's not a tangible physical substance. Instead of discrete particles, it's energy itself, arranged in a stable configuration. And the protons and neutrons inside the nucleus, they're held firmly by the strong force's residual power. They neither directly touch nor are they physically glued together. They are in fact captured within a potential well, which is generated by the exchange of particles called pions. But pions themselves are made of quarks. Ultimately, it's quantum fields reaching down to the very foundation. So let's take a moment to ask the question again. What truly resides within an atom? Not discrete particles, not tiny spheres, not static orbits, not palpable matter. The actual contents of an atom are fields, quantum fields to be precise. We have the electron field, the quark field, the gluon field, and the electromagnetic field. These fields permeate all of space. They are present everywhere at every moment. To say an electron is within an atom means the electron field displays a localized excitation near the nucleus. An atom is not a solid object. It is instead a pattern. A stable configuration of field excitations sustained by forces that are themselves propagated by additional field excitations. At the most fundamental level, no solid objects truly exist. There is no matter, only fields persist. And these fields are simply mathematical constructs that assign numbers to each point in space and time. These numerical values evolve according to differential equations, sometimes producing localized excitations we call particles. I imagine this might be a challenging concept to grasp. I comprehend it. There's a deep human longing for an ultimate reality, a firm foundation, something you can precisely identify as its final composition. Nevertheless, it proves undiscoverable. Instead, our discoveries reveal only mathematics, elaborate equations, intrinsic symmetries, and foundational conservation principles. Remarkably, these mathematical principles somehow give rise to the illusion of tangible objects, tables, chairs, and even your own physical being. Each and every entity is an intricate weave of patterns within quantum fields, constrained by fundamental forces, stabilized by exclusion rules, and perpetually phasing in and out of existence trillions of times each second. Now, allow me to present another revelation that could very well disquiet you. Essentially, the atom is overwhelmingly composed of empty space. You've probably heard this before, yet even that perception is inaccurate. The region we designate as empty space is, contrary to popular belief, far from being a true void. Those omnipresent quantum fields still fill that expanse. Ephemeral virtual particles are constantly flickering into and out of being. The vacuum itself pulses with a vibrant maelstrom of activity. Beyond that, the electron's wave function pervades the atom's complete spatial extent. Its presence is determined by a non-zero probability amplitude existing throughout the atom's entire structure. Pressing against a table doesn't involve the sensation of particles actually colliding. Instead, what you perceive is the electromagnetic repulsion between electron clouds, which are field configurations actively resisting any attempt at interpenetration. The Pauli exclusion principle is at work here, preventing electrons from sharing the same quantum states. This imparts a feeling of solidity because the forces involved are incredibly strong, despite there being no actual physical contact, no direct touching whatsoever. It's simply fields exerting pressure upon other fields. Our conventional understanding of size utterly collapses, and it's precisely here that our intuition about the universe proves entirely inadequate. Consider this: the atomic nucleus is an astonishing 100,000 times more diminutive than the atom's overall structure. To truly comprehend this immense scale, imagine magnifying the nucleus to the dimensions of a mere marble. The atom would then swell to encompass an entire football stadium. Yet what follows is perhaps the most astounding revelation. The electron itself, according to every observation we've made thus far, appears to possess absolutely no discernible physical dimension. It exists fundamentally as a point-like entity. Without exception, every experiment performed has consistently produced data pointing to a dimension of precisely 0. Thus we are presented with a point particle, entirely lacking in spatial extent, yet inexplicably managing to occupy a defined region spanning a diameter of 10 to the power of minus 10 meters. Does such a paradoxical concept truly align with our logical understanding? No, it unequivocally defies our conventional logic naturally. Nonetheless, these represent the incontrovertible realities that our scientific investigations persistently bring to light. It seems nature remains utterly indifferent to whether its fundamental principles conform to the limits of human comprehension. And now we shall explore a concept that renders this situation even more bewildering. Our focus now shifts to the mysterious characteristic referred to as spin. Electrons possess a fundamental inherent attribute known as spin. This attribute functions similarly to angular momentum, creating the illusion of a rotating electron, despite the electron definitively not spinning. It is inherently unable to spin precisely due to its existence as a point-like entity. A point by its intrinsic nature lacks any spatial dimension and consequently cannot experience any form of rotation. There is absolutely no physical substance within it to facilitate spinning, and yet in a profound paradox, the electron undeniably exhibits angular momentum. It possesses an intrinsic angular momentum, a characteristic not stemming from any actual physical rotation. This is merely a fundamental attribute of the electron, much like its electrical charge or its mass. The designation spin is employed because it exhibits the mathematical properties of angular momentum, even though it doesn't signify genuine physical rotation. This fundamental property, known as spin, is quantized, existing specifically at a value of 1/2. Should you measure it along any arbitrary axis, you will consistently observe one of two results: either up or down, with no intermediate states ever appearing. However, prior to any measurement being conducted, the spin itself holds no definitive direction. It resides in a state of superposition, and the mere act of measuring its orientation along one axis makes its state indeterminate along any axis perpendicular to it. But what is the underlying reason? That particular question continues to elude a definitive answer. This is simply the intrinsic nature of how quantum spin fundamentally operates. No phenomenon encountered in our everyday experience exhibits such a peculiar mode of behavior. The energy levels present within an atom are likewise subject to quantization. Electrons are constrained to possess only certain distinct energy values, never merely any arbitrary amount of energy. Only well-defined, discrete values are permitted for them. What is the underlying explanation for this phenomenon? This arises from the requirement that the electron's wave function must precisely conform to the spatial confines surrounding the atomic nucleus. A highly fitting analogy can be drawn with a vibrating string. A string is only capable of oscillating at specific allowed frequencies, its fundamental tone and its various harmonic overtones. Precisely the same principle applies to the electron's wave function within the atom. Only specific wavelengths are permissible, and given that energy is intrinsically tied to wavelength, this inherently dictates that only certain discrete energies are allowed. The moment an electron shifts between its discrete energy states, it either releases or absorbs a photon, the energy of which perfectly aligns with the exact difference between those two levels. This very phenomenon illuminates why atoms radiate light at precise wavelengths, beautifully illustrating hydrogen's signature red and blue spectral lines. Each distinct line on the spectrum vividly portrays a unique quantum leap between disparate energy levels. We can determine these wavelengths with truly astonishing precision, and quantum mechanics empowers us to predict them with an equally astounding level of accuracy. The harmony between theory and observation stretches to an incredible 10, 12, or even 14 decimal places. Clearly, the theoretical framework stands robust. But what truly underpins this remarkable quantization of energy levels? The intricate mathematical calculations reveal the profound answer. While experimental observations confirm this truth, a more fundamental explanation remains elusive. Now let's delve into the fascinating repercussions of trying to glimpse inside an atom. Using visible light is simply out of the question, as its wavelength is far too large compared to the atom itself. Instead, we need something with a much shorter wavelength and consequently far greater energy. Yet here we encounter a profound dilemma. The very instant you unleash high-energy probes to observe an electron, you inescapably disturb its state. You effectively knock it right out of its initial quantum state. The mere act of observation fundamentally changes the very phenomenon you set out to measure. This isn't simply a technical hurdle to overcome. Instead, it reveals a deep foundational principle of nature. To truly observe objects of such minute scale, one absolutely requires illumination with a short wavelength. A shorter wavelength, by its very nature, indicates a more substantial energy. These amplified energy magnitudes are bound to induce significant perturbation. This particular consequence is utterly unavoidable. The mere act of measurement inherently reshapes the system itself. Within the quantum domain, truly passive observation proves to be an impossibility. Consequently, we cannot pinpoint an electron's location before measurement. It's not simply obscured, but rather the property of occupying a precise spot only materializes when a measurement is performed, thereby bringing that specific characteristic into being. Prior to any observation, the electron's condition is defined by a wave function encapsulating a superposition of every conceivable reality. Following a measurement, the electron undergoes a collapse into a singular definite state, manifesting as one of those previously available possibilities. The process of measurement doesn't simply uncover a reality that was already in existence. Instead, it actively shapes a tangible reality from an indeterminate one. Therefore, what exactly is contained within the boundaries of an atom? It is neither tiny spheres, nor predetermined orbits, nor solid matter, nor even distinct particles in the... The atom's fundamental nature is a mathematical entity, a wave function, which is a solution to the Schrödinger equation, an intricate pattern of probability amplitudes that indicates what one will perceive upon observation, but provides no description of a static reality when unobserved. An atom functions as a quantum system, and these systems display behaviours utterly distinct from anything in our conventional daily experience. Their very being is characterised by states of superposition. They possess inherent characteristics that are, at their core, indeterminate. They intrinsically defy any form of direct mental visualisation. One cannot mentally picture an atom's inner structure precisely because there is no tangible object to visualise. Significantly, the wave function is not a physical wave that exists within conventional space. Instead, it operates within an abstract mathematical realm specifically designated as Hilbert space. What we observe here is a progression of complex numerical values serving as a sophisticated code for various probabilities. It embodies unadulterated information entirely distinct from any physical, tangible substance. And yet, the entirety of our physical cosmos emerges directly from this abstract mathematical construct. From the fundamental laws of chemistry to the complexities of biology and even the very essence of consciousness, all are intricately woven from patterns within quantum fields. These are governed by precise equations, adhering to principles that often defy our everyday intuition, yet operate with astonishing, undeniable accuracy. The genuine essence residing within an atom isn't particles or mere stuff, as we commonly conceive it. Instead, it is pure mathematics. Mathematics in its most pristine theoretical manifestation, aesthetically profound yet utterly unfathomable to our minds. And if this explanation fails to fully satisfy you, if you still yearn for something more, something tangible and truly fundamental at the very core of existence, then I must offer my apologies. However, the vast cosmos remains entirely indifferent to your personal desires or expectations. Its inherent nature simply is what it is, and that underlying reality proves to be far more peculiar than you could have ever possibly envisioned.